In this video, I'll show you how to make a PWM from scratch, and we will use a half bridge for this. So let's start. So first we need a voltage source. So we can just write a voltage, and this should be on the input. And then I have already predefined a voltage, which is called Vn. And then we can use an IGBT. So I will use those with diodes, so it works in both directions. So we can just connect that to the battery. So we can just connect that to the DC link voltage, the input voltage. And then we have another that we connect also to the DC link voltage. So now you can see that we basically have the topology that we want. So then we can also add a voltage measurement. So here we have a half bridge, and then we measure the output voltage in reference to, so this is the ground. We can just add a ground, just to be clear about that. This is where we want to reference all of our measurements. It doesn't matter, we don't need the ground in Simulink. And now we need to make the PWM. So we can first add the gate signals. So we have a from, where the gate signal comes from. So it should be, let's just call it S for gate signal. And then it goes into the gate signal there, into the switch there. And then this one should be inverted, so we can use an inverter. No, it's called not. I think it's called not. So we'll use that to invert the gate signal. So now we need to generate the gate signal. So we use that with a PWM. So I have a PWM here in this document. There it is. So we just need to make this. So first we can define a duty cycle. So let's just add a constant for that for now. And let's just set it to 0.5, which means a 50% duty cycle. And then we need a comparator. Here it's called relational operator. And then I want to change the sign. So we have like this. And now we need a carrier. So then we want I think it's called a sequence generator, something like that. Repeating sequence. Then we insert that to the other end of the comparator. So now, you can see that when the duty cycle is larger than the carrier, we get 1, which is exactly what we want. So now we want to make a triangular waveform. So we need to add some time samples. So after a half period, which is 0.5 over the switching frequency, so I predefined a switching frequency here. And then we want to add another sample after 1 period. So at 0 time, it should be 0, and then after 1 half period, it should be 1, and then after 1 period, it should be 0. So then we get a triangular waveform. So this should work. So now we can try to run it. Yeah, you can see that we missed the power GUI. So I'll just add that. And it should actually not be continuous because we have the carrier, which is very fast. So we can add, 1 microsecond is great. So now if we run that, you can see that we have a bit too large of a step time. So we can change that to 0.01. Then we can run it again. I forgot to add some scopes as well, so we need to add that as well. Scope, so that we can see the measurements. So now you can see that it's, on average, a 50% duty cycle. So now the duty cycle is defined as the desired output voltage, which we just called Vref, over the input voltage. So we can define the duty cycle as such instead of this block. So we can add a divide. which we add here, and then we can add the reference voltage that we want. So we have, let's say 300. And then we can add the input voltage. And this should be 400. So if we add a measurement on, we can actually add all of these signals here. So we can add the carrier as well. Then we can also add, can we add that one? We can just make it larger, then we can add it. The gate signal, just to see all of them at once. So now you can see that the carrier is the blue one here, and then we have the gates, the duty cycle is the yellow one. So you can see that it's approximately 75%, which makes sense because 300 divided by 400 is 75%. And then you can see that the gate signal is on approximately 75% of the time, which makes sense. And then we get an output voltage, which is an average 300 volts. Now we can actually add a moving average to filter this output voltage. So I will just make sure that we see both at the same time. Just move it a bit out there. And now we need to decide the filter constant. So we can take that as, let's say, half of the switching frequency. That should work well. Now you can see that it is actually indeed 300 volts, which is what we wanted as the reference voltage. And now this works for any type of reference voltage, which is between 0 and the input voltage. So let's say that we add a sinusoidal signal instead. Sine wave. And then let's say that the amplitude is, let's say 300. And then we need to add a switching frequency, as well. Let's say 50 Hertz. Then we can increase so we view exactly one period. That was not one period. What did I do wrong here? 50 Hertz. Yeah, because this is in radians. So we have to multiply by 2 pi. Then we should get one period. So you can see that it works fine for the first half of the period. Then we get an average, a sinusoidal signal. But when the duty cycle becomes less than 0, then the PWM doesn't work because it's outside of the carrier. So we need a signal which is between 0 and 1, a duty cycle which is between 0 and 1, which means that we need a reference voltage between the input voltage and 0. So if we change that, we can add, let's say that the amplitude is instead 100. Then we can add bias of 200. Now this should work. And now you can see that works because we have an average 200, the bias is 200, and then the peak, the amplitude is 300, and then we have a sinusoidal signal. So you can see that it worked very well to make this voltage that we wanted. So this is basically how a PWM works. And if you want to understand the mathematical background, you can watch my other video on that, where I explain with this document. And if you want the document, which is a mini course on different PWM strategies for a full-bridge inverter, then you can go in the link in the description.